Hello, welcome to another practice problem. Today we're going to solve problem 5.27 out of the textbook, and we will be using the textbook method to solve this. The given problem statement: section 1 is an aluminum pipe with a modulus of elasticity of 10 ksi or 10,000 ksi, cross-sectional area of 4.5 inches squared, and member 2 is a steel pipe, modulus of elasticity of 30,000 ksi and a cross-sectional area of 3.2 inches squared. So there's a fixed support at both ends of the assembly, and we're asked to find the normal stress in the aluminum pipe and the steel pipe and the deflection at flange B. So using the textbook method, what I'm going to do is I'm just going to go ahead and make a free body diagram, but I'm going to make my cuts through the members right here, and then just make a free body diagram of the centerpiece. So my free body diagram is going to have the flange in the center with the steel rod from one side and the aluminum off the other. We have our 45 kips on each side. And then we have reaction forces. So we have right here, because this is on member 2 and this is pipe 2 and pipe 1, I'll call this F2, and we'll call this F1. So what we can do is we can do some of the forces in the x direction equaling 0, and that being my positive. We can then say negative F1 plus F2 plus 90 kips equals 0, right? So there's what we can identify as equation 1, right? And we know, since if we go back to our original drawing, the diagram, there's a fixed support at either end of this system, meaning that once this 90 kips is applied, 45 on each side of the flange, that there's going to be deflection of each member, right? Member 1 and member 2. However, the summation of those two deflections has to be 0 because they're a fixed support. So we can have another equation. Our deflection of 1 plus deflection of 2 has to equal 0, right? So what we can do is rewrite that is the force in member 1 multiplied to the length, area, modulus of elasticity, plus the force of member 2 and its length over area and modulus of elasticity, all equals 0. And this we can call equation 2. So what we can do now is solve equation 2 for one of the forces. So I'll just go ahead and solve for force 2, because now we have two equations and two unknowns, right? Because the lengths, modulus of elasticity, and areas are known, and 90 is a constant. So just solving this and doing algebra, we can say F2 equals negative F1, length 1, area 2, E2 divided by area 1, modulus elasticity 1, length 2, and then just taking this relation and plugging it into here, and then solving for F1. I'm not going to do all the algebra here, but solving for F1, if you do it correctly, you could get a force of F1 to equal 35.273159 kips. And then from this, with this answer, we can plug it back into this equation and solve for F2. So F2 then equals negative 54.726841 kips. Okay? So with these two known forces, what we can do now is find the stresses in each one of our members, right? And verify that this makes sense, right? So force 2 is negative, right? Which makes sense because if we have 45 kips here and here, that's a compressive force acting on member 2, right? And so it's a negative. And then this would be a tensile force acting on member 1, right? So it's tension. It's going to be our positive value. Those just make sense, right? So now what we can do is find our stress of member 1 equals the force of 1 divided by the area of 1. So stress of 1 then equals 5.273159 kips divided by our 4.5 inches squared, and that should equal 7.4 kips per square inch, and this is in tension. And so that's our stress for member 1. So doing the same method for the stress in member 2, you should get the stress in member 2 to equal 17.10 KSI. And this, again, like we mentioned, is in compression. So we know our force and the length and area and modulus of elasticity for each member. So going back and using one of these deflection relationships, we can solve for our deflection of the flange B. So what we can just say is we'll use the positive value, so the deflection of 1 is going to equal the force of 1, length of 1, divided by area of 1, modulus of elasticity of 1. And this, plugging all the values in. Remember, units are important, so I'll just write this out. We have 35.27 kips multiplied to 160 inches divided by 4.5 inches squared multiplied to 10,000 kips per square inches, and this should equal 0.1254 inches moving that direction. And that's your deflection of flange B.